everyone, thank you so much for joining this video. Today's learning objectives are to know that transition metals and their compounds can act as heterogeneous or homogeneous catalysts, to know that a heterogeneous catalyst is in a different phase from the reactants and that the reaction occurs at the surface of the catalyst, and to understand in terms of oxidation number how V2O5 acts as a catalyst in the contact process. We're then going to understand how a catalytic converter decreases carbon monoxide and nitrogen monoxide emissions from internal combustion engines by adsorption of carbon monoxide and nitrogen monoxide molecules onto the surface of the catalyst, and weakening of bonds in chemical reaction, and desorption of carbon dioxide and nitrogen product molecules from the surface of the catalyst. We're then going to know that a homogeneous catalyst is in the same phase as the reactants, and appreciate that the catalyzed reaction will proceed via an intermediate species, and to understand that the role of Fe2 plus ions in catalyzing the reaction between I- and S2O8 2- ions, and to know the role of Mn2 plus ions in autocatalyzing the reaction between MnO4- ions and C2O4 2- ions. We're then going to look at a core practical, which is the preparation of a transition metal complex. Now we're going to talk a bit about catalysts. A catalyst is a substance that provides an alternative route for the reaction with a lower activation energy, so it increases the rate of reaction without being used up in the reaction. And how it increases the rate of reaction is because it's provided this lower activation energy route. That means that more of the particles will have the activation energy required to successfully collide, and so the rate of reaction will increase. So there are two types of catalyst. The first is heterogeneous, and this means the catalyst is in a different phase to the reactants. And the second type is homogeneous, which is a catalyst that is in the same phase as the reactants. And so firstly, we're going to look at the heterogeneous catalysts. So there are a few things you need to know. The first is that they're usually solids and the reactions take place at the surface of the catalyst. Most industrial processes use these kinds of catalysts. For example, in the Haber process, when we produce ammonia from hydrogen and nitrogen. We also use support mediums, and these are often ceramic honeycombs, to maximize the surface area of a heterogeneous catalyst and minimize the cost, because we need to use less of the catalyst because we only need a thin layer over these support mediums, and because they have a massive surface area, that means that the rate of reaction will increase further. And at least one of the reactants is adsorbed onto the surface of the catalyst, onto an active site, and then it can react with another reactant. And then the product then desorbs from the surface of the catalyst. So this is how a heterogeneous catalyst works. And it's really important to remember that the reactants are adsorbed and not absorbed, because absorbed means it's going into the surface, but adsorbed means it's just going onto the surface. So bonds are formed between the reactant and the surface of the catalyst, or very weak bonds. And after that, the reactant then meets another reactant, and then they react together, and then the product formed will then desorb, which just means detach, basically. It desorbs from the surface of the catalyst, and that's basically how a catalyst works. Now, the adsorption increases the number of reactions by a number of reasons. The first is that it concentrates the reactants. So it basically makes all the reactants come together into the same kind of area. So there is more chance of them reacting with each other. And then the adsorption also weakens some of the bonds in the molecules. And so that also makes it easier for them to react. And the third thing is that they position the molecules in favorable orientations for reaction, because actually for successful collisions of particles, they actually need to be in the right orientations in order to react. However, there are some problems if the adsorption isn't just right. So if it's too weak, the catalyst will have very little effect, as not many molecules will be adsorbed. So not many molecules can form bonds with the surface of this catalyst. And also, if the adsorption is too strong, then the molecules won't be able to move around the active site, so they'll be less likely to find other reactants to react with. And also, the product formed will not be able to desorb, so the product formed will not be able to detach itself from the surface after reaction. So the molecules are not able to move around, and so there's less likely chance of reactions happening, and also the product formed will not be able to desorb. So now we need to look at some examples of these kinds of catalysts that we need to know. So the first is vanadium oxide, and vanadium oxide is used in the contact process, and so the key step that we're trying to speed up is the conversion of sulfur dioxide to sulfur trioxide, because this can be quite slow. And so in the first step, we have the vanadium oxide reacting with the sulfur dioxide to form V2O4, and we call this V2O4 an intermediate because it's being produced in the first step, but all used up in the second process. So it doesn't actually come into the overall equation. And so this V2O4 then reacts with some oxygen to reform the vanadium oxide. So this is what we mean by the catalyst remains unchanged throughout the reaction. So this means that you can use it again and again, reacting more and more of this sulfur dioxide to form sulfur trioxide. And the overall equation we get is that sulfur dioxide combines with half a molecule of oxygen to form sulfur trioxide. And it's really, really important that you remember all these equations, this for step 1 and step 2, and also the overall, because they quite regularly ask you. And the second example we need to know is that iron is used in the Haber process to produce ammonia. So we have nitrogen and hydrogen, and then we have solid iron also on the support medium, the honeycomb, to speed up the reaction to form ammonia. And a really important thing also to know about catalysts is that they speed up the time it takes to get the reactions to equilibrium, because this reaction here is actually an equilibrium. So the catalyst speeds up the time it takes to get to that equilibrium, but it does not change the equilibrium. So it doesn't shift it to the left or to the right, because catalysts have no effect on equilibria. And also we need to know about the poisoning of these heterogeneous catalysts. So they can become poisoned by impurities that basically block off the active sites of these catalysts, and consequently they reduce efficiency, and this has a cost implication. So these are two examples that we have to memorize. So the first is that we get lead poisoning of catalytic converters in cars. So both the rhodium and platinum catalysts are poisoned by lead, and they're really, really expensive to replace. And the second example we have is sulfur poisoning in the Haber process. So the hydrogen, which goes into making the ammonia, is obtained from natural gas, and it might be contaminated with sulfur before, and so the sulfur will poison the iron catalyst if it's not removed, and that's also very expensive to replace. So we need to remember lead poisoning of catalytic converters and sulfur poisoning in the Haber process. Now we're going to talk about catalytic converters. So we're going to look more into how heterogeneous catalysis works in catalytic converters. So the first thing that happens is that the carbon monoxide and nitrogen monoxide molecules, which come from the car exhausts, form bonds with atoms at active sites on the surface of this heterogeneous catalyst. And so they are adsorbed onto the surface. So as a result, bonds in the reactants are weakened and they break. And so new bonds form between the reactants held close together on the catalyst surface. And after they react, desorption occurs, where the carbon dioxide and nitrogen product molecules are removed from the surface of the catalyst. And now we're going to look at homogeneous catalysts. So most reactions with homogeneous catalysts usually take place in solution, and these reactions have to proceed via an intermediate species. And this is formed from a reactant and the catalyst, which then reacts further and regenerates the catalyst. And so it is really important for a catalyst to have variable oxidation states, and this is why we use transition metal compounds to catalyze reactions. So now we're going to look at some examples that you need to know. The first is the role of Fe2+ ions in catalyzing the reaction between iodide ions and also peroxodisulfate ions. So the reaction is very slow because it involves the reaction of two negative ions, and so the I- and the peroxodisulfate ion repel each other. And this is why it's catalyzed by Fe2+ and Fe3+ ions. Fe2+ and Fe3+ can easily change between the oxidation states, and so that's why it acts as a catalyst, and that's why it's good at doing that. So in the first step, Fe2+ reacts with the peroxodisulfate ion to form Fe3+ and sulfate ions. And then in a second step, the intermediate, which is this Fe3+, reacts with the iodide to reform Fe2+ and iodine. And so overall we get the equation, and so overall we get the reaction of an iodide reacting with peroxodisulfate to form iodine and sulfate ions. And these reactions can actually occur either way round. So for this particular way we've done it, this Fe3+ is acting as the intermediate species because it's produced in step 1 but used up in step 2. However, if we did it the other way round, then the Fe2+ would be the intermediates. The second example we need to look at is the autocatalysis by Mn2+ ions in the reaction between manganate ions and ethane dioate ions. So again, the reaction is very slow as it involves the reaction of two negative ions that repel each other. And so it's catalyzed by Mn2+ ions as it easily changes between oxidation states +2 and +3. So they're the oxidation states of the manganese. And the catalyst is the product of the reaction. So the reaction is slow until Mn2+ starts to be produced, and then it speeds up. And this is why we also call it autocatalysis, because the catalyst is actually the product of the reaction that we're doing. So in step 1, Mn2+ reacts with MnO4- in acidic conditions to form Mn3+ and waters. And then in the second step, Mn3+ then reacts with the ethane dioate ions to form carbon dioxide and also to reform the catalyst Mn2+. And so the intermediate in this case would be this Mn3+ because it's being produced in the first step and being used up in the second step. So overall we have that 2 manganate ions react with 5 of the ethane dioate ions in acidic conditions to form Mn2+ ions and water and carbon dioxide. So when we say about autocatalysis, it's because this Mn2+ is formed from the reaction. And so when this first starts to occur, it's very, very slow because we have these two negative ions repelling each other, but they're trying to collide. And then as soon as this is formed, we can then start these two processes. And so the reaction will begin to speed up. Now we're going to look at a core practical, which will be the preparation of a transition metal complex. So the overall method is this. The first step is to use the weighing by difference method to accurately weigh out a mass of copper sulfate between 1.4 to 1.6 grams into a test tube and add 4 centimeters cubed of water. So the weighing by difference method is when you weigh the weighing boats separately and then you add in the copper sulfate and then you weigh it again and then you take the difference. The second thing you do is you fill a large beaker with freshly boiled water and rest the test tube containing copper sulfate and water in it, and you stir until the copper sulfate has dissolved. And then the third step is to add 2 centimeters cubed of concentrated ammonia in a fume cupboard. And then what you do is stir the mixture and pour into ethanol, and then cool the mixture in an ice bath, and crystals of the product will form. You then set up a vacuum filtration apparatus with a Buckner funnel and collect the crystals in the funnel. You wash the tube with a cold ethanol and filter again, and then the crystals you wash with cold ethanol. You then leave the crystals on the funnel for a short amount of time to dry, and then press a second piece of filter paper on top of the crystals to dry them even more. And then you record the mass of the crystals and calculate the percentage yield. So we have a setup kind of like the diagram on the right, with the Buckner funnel above the Buckner flask and the vacuum pumping all the air out. Now we're going to look at a quick question. So a cleaning agent called Barkeeper's Friend contains ethane dioic acid as the active ingredient. 2.34 grams of the powder was dissolved in water and made up to 250 centimeters cubed in a volumetric flask. 25 centimeter cubed portions of this solution was acidified with sulfuric acid and reacted with 27.75 centimeters cubed of 0.00300 moles per decimeters cubed of potassium manganate on average in a titration. Calculate the percentage by mass of the ethane dioic acid in the cleaner. So first what we do is we work out the equation for the ethane dioic acid and the manganate. So we know that C2O4 minus is turned into carbon dioxide. And so now we can begin to balance. So we need 2 carbons. And then we'll have to balance the 2 minus charge, so we'll need 2 electrons on this side. And then for the manganate, we have MnO4 minus, and then we turn this into a manganate 2 plus. And so we need to balance the oxygens first. So we have 4 waters, and then we have 8 hydrogens on this side, and then we balance the charges, and we do that by adding 5 electrons to this side. And so now we can form the overall equation. We have 5 of these ethane dioates reacting with 2 of these MnO4 minuses plus 16 H pluses to form 10 carbon dioxides and 2 of these Mn2 plus ions and 8 waters. And if you've forgotten how to write these half equations and to combine them, then quickly go back to the redox. Alternatively, you could have just remembered this equation. So after doing lots and lots of these questions, you might actually already remember it without having to construct the full equation from the 2 half equations. So then what we do is we work out the number of moles of the potassium manganate were needed in the titration. And so we can have the moles of potassium manganate is equal to concentration times by volume. So we've got concentration of 0.00300 and then a concentration of 27.75 centimeters cubed. And this gives us 8.325 times 10 to the minus 5 moles. And then therefore, looking at the equation, we can see that the ratio between manganate and ethane dioate is 2 to 5. So that means that the moles of this ethane dioate that reacted would be in the ratio of 2 to 5 with this number of moles. So therefore, it's equal to 5 over 2 multiplied by the number of moles of potassium manganate. And so we get 2.08 times 10 to the minus 4 moles. But we need to remember that this is in 25 centimeters cubed. And that's a really key thing to remember, because that means we need to multiply it up. So that means that the moles of C2O 2.08 times 10 to the minus 3 moles. And so now we can work out the mass. So the moles of this C2O4 minus must be equal to the moles of this H2C2O4. So now we can work out the mass of H2C2O4, and this will be equal to moles times molar mass. So we've got 2.08 times 10 to the minus 3 moles times by the molar mass, which is 2 plus 24 plus 64, and this comes out to be 0.187 grams. And so percentage by mass, how we work that out is we do 0.187 over the total mass, which is 2.34 grams, and then multiplied by 100, and so this gives us 7.99%. And now we're going to have a look at another question. So before I start, feel free to click off the video and try it for yourself first. So it tells us to calculate X in the formula FeSO4XH2O from the following data. 12.18 grams of iron 2 sulfate crystals were made up to 500 centimeters cubed, acidified with sulfuric acid in a volumetric flask. 25 centimeters cubed of the solution required 43.85 centimeters cubed of 0.0100 moles per decimeters cubed of potassium manganate for complete oxidation. So what we do first is write out the equations. If you've already memorized them, then you don't need to do this step. But I always quite like to do the half equations and to then combine them to make the full equation. So I definitely know that I've got it right. So we know that MnO4 minus ions are reduced to Mn2 plus ions. And now we need to balance it. So first we balance the manganese, and they're already balanced, so we can ignore that. And now we balance the oxygens by adding water. So we need 4 waters, and that means we need 8 H pluses because we've got 8 hydrogens on the other side. And now we need to balance the charges by using electrons. So on the left-hand side, we've got a charge of +7, and on the right-hand side, we've got a charge of +2. So that means we need 5 electrons on the left. And now we need to balance the Fe2 plus Fe3 plus equation. So we have Fe2 plus, and if we remove an electron, we get to Fe3 plus. So these are the two half equations, and now we combine them to make the overall equation. And we can see that the ratio is 5 to 1, and so we need to multiply the second equation by 5. So what we have is that we have MnO4 minus plus 8H plus 5 Fe2 pluses, and then this forms Mn2 plus 4H2O plus 5 of these Fe3 pluses. And this is our overall equation. And we're going to use this to work out. And so now what we do is we work out the number of moles of manganate that we have. So in other words, we work out how many moles of the potassium manganate we have. And so the moles of manganate ions is equal to concentration times by volume. So we have concentration of 0.0100 and multiplied by the volume, which is 43.85 times 10 to the minus 3, because we need to convert it to decimeters cubed. And so we get 4.385 times 10 to the minus 4 moles. And now we look at the equation. So we know that manganate and Fe2 plus react in a 1:5 ratio, and that means that we must have reacted 5 times this amount of the Fe2 plus ions. So the moles of Fe2 plus is equal to 5 times 4.385 times 10 to the minus 4. And this gives us 2.1925 times 10 to the minus 3. And now we need to remember that this is just in 25 centimeters cubed. Because in the question, we only titrated it with, we only titrated 25 centimeters cubed of this FeSO4XH2O with the manganate. And so this means that we need to times this number in order to get it to 500 centimeters cubed, like how it was originally. And so we have the moles of Fe2 plus 500 centimeters cubed is equal to 20 times by 2.1925 times 10 to the minus 3, because 500 is 20 times bigger than 25. And so this gives us 0.0385 moles. And this is also the moles of FeSO4XH2O we have, because in this formula we have 1 mole of Fe2 plus for every 1 mole of this compound. And so we have that. And so therefore, the moles that we have of this Fe FeSO4xH2O is equal to 0.04385. And so now what we can do is we can work out the mass. And in order to work out the mass, we need the MR. And so now we can work out the MR. So for the MR, we need the amount of moles and the mass. So the mass is given in the question as 12.18. And so we have the equation moles equals mass over MR. And therefore, rearranging this, we have MR is equal to mass over the moles. And so MR is equal to 12.18 grams over 0.04385. And this is equal to 277.8. So this is the MR of the whole compound, so FeSO4xH2O. And so now we need to take away the MR of FeSO4 to get the MR of xH2O. So the MR of FeSO4 is equal to 55.8 plus 32.1 plus 16 times 4, and this is 151.9. So then now we know the MR of xH2O. So the MR of xH2O is equal to 277.8 minus 151.9, which is 125.9. And now what we do is we work out the MR of H2O and then divide it so we can find how many H2Os we have, so how to find X. So the MR of H2O is equal to 1 plus 1 plus 16, which is 18. And so X is equal to 125.9 divided by 18. And this gives us 6.99 ... So therefore X is equal to 7 because we round it up.